Well, we're very happy to have for this week Surena Hozoori from Georgia Tech speaking on contact and symplectic geometry of Anosov flows and their invariant volume forms.
Okay, thank you, Catherine. First, let me thank all the organizers for this great opportunity. This is my pleasure to present for such great audience. So today I'm going to talk about some interactions between contact and symplectic topology and hyperbolics in low dimensions, in particular Anosov flows in dimension 3. Anosov flows more or less kind of like a contact and symplectic geometry. They're known to have very subtle and deep relation to geometry and topology of the underlying manifold. And my goal today is to discuss how, as a contact geometer or symplectic geometer, I would approach these flows. I'm going to start. I'm going to start with some like basic background on Anosov 3 flows. I'm not going to assume that there is any prior knowledge in the audience that much on the topic. After that, I will discuss a geometric characterization of these flows purely in terms of contact and symplectic geometry. And then I will discuss how the existence of an invariant volume form, what it would like imply about the picture that I'm painting. And finally, I'll try to basically connect this characterization to various subfields in contact and symplectic geometry, like Reeb flows, Liouville geometry, contact surgeries, and so on. So, okay. During this talk, I'm going to assume that M is a closed-oriented and connected 3 manifold. X is a non-vanishing smooth vector field on M, and phi is the flow generated by X. And let me also mention that most, not all, but most of the things I discussed there, you just see one regularity of the vector field is enough. But for simplicity, I'm going to assume that the flow is smooth. So let me just start with the definition of Anosov flows. They were introduced in early 60s by Dmitry Anosov. The flow phi is called Anosov if there exists a splitting of the tangent space of the manifold into 3 line bundles, ESS, EUU, and X, which is the direction of the flow, such that the splitting is continuous and invariant under phi. And if you just take a vector, let's say in EUU, look at the action of the flow on that vector, you will see that the length of that vector would increase exponentially. And similarly, if you take a vector in the ESS line bundle and apply look at the action of the flow on that vector, you will see that the length of that vector would decrease exponentially. Here, C is a constant, and I'm also using a norm on the manifold, which is induced from some Riemannian metric. So we call these 2 line bundles, they have names. We call them strong, stable, or unstable directions. Stable is for the one where the length is decreasing, and unstable is the other one where you have like this expansion type of behavior. And also let me mention that although the flow is smooth, the splitting is usually only C0. Actually, in many situations, we can show that we can't really have anything better than C0. Okay, so there's a picture that you all have seen, which kind of encapsulates the hyperbolic dynamics. So the definition suggests that you have like this kind of expanding behavior in the EUU direction. And you have this contracting behavior in the ESS direction. And that would basically force the behavior of the action of the flow on the rest of the tangent space, like this. And you see this kind of hyperbolic picture that I'm sure you've seen. Okay, so Okay, so let me give you a few examples. So there are two very classical examples of Anosov flows. As a matter of fact, for a quite long time, it took quite some time for like new, like essentially like new and like inequivalent Anosov flows to be introduced. One of them is the suspension Anosov flow. So consider an Anosov diffeomorphism of torus. Remember that this means that this is like some area preserving like linear map, such that the eigenvalues, you have like one eigenvalue bigger than, with absolute value bigger than one, and the other one less than one, right? So that means like you can think of F as a member of SL2Z. I think an example would be given by this matrix, if I remember correctly. And you can, the same way that you can define, you know, this like torus bundle of like this map, you can also induce some sort of flow on this map. So what we're doing is that we define M as like this torus. Oops. We are like, if we have like this torus times interval. So this is like torus times interval, and we have like these flow lines, which are just this vertical kind of lines, segments connecting the two sides. And if you take one point and look at its trajectory, it will just move like vertically to hit a point in t cross, let's say 1. Let's call that x, and then we just glue this using the map f to another point f of x, and continue the flow line from here, and so on. So we use this kind of this gluing map in order to not only you know, build the manifold, but we will also induce some sort of some sort of flow on it, which can be seen is Anosov if that diffeomorphism is Anosov. And another and somehow like even more classical example is the example of geodesic flows. That was the example which was studied by Anosov himself as some sort of motivation. If it turns out that if you take a hyperbolic surface, that you will have a geodesic flow introduced on the kind of unit tangent space of sigma, which is a 3 manifold, and the geodesic flow would be Anosov if the metric you have is hyperbolic. Okay, so these are the two classical examples. And before moving on, let me mention that most of the connections to topology in low dimensions are explored thanks to the use of foliation theory. It started in, I guess, 70s in the work of Thurston, Ponte, and Verjovsky, and many more. And so how do we use foliation theory in this context? That's by noting that if you just take one of these line bundles, stable or unstable, and add the direction of the flow, well, of course, you will get a plane field. Let's call that ES. And it turns out that this plane field is tangent to some foliation. And we call that this foliation, the stable foliation of the flow. Let me just mention that, it's very easy to see that these plane fields are integrable. Anosov himself showed that they're uniquely integrable. And it took around like more than 30 years to show that these plane fields are in fact C1, which is something that I will use. And I just want to emphasize that that's really like not trivial that these plane fields are C1, but that's a feature that will definitely help us as we go towards the contact and symplectic geometry, where we expect the objects to have at least some regularity. And if I want to draw a picture for you for these foliations, you can look at how these foliations look like in the neighborhood of a let's say a small trajectory. So that means that this flow line lives in the intersection of two foliations. One of them is the stable foliation, the other one is unstable foliation. So here's kind of like the picture. And on this, on the, let's say this is unstable foliation. And on this unstable foliation, you have this kind of expanding behavior around that orbit. So the flow lines are kind of running away. And on the stable foliation, the flow lines are kind of being sucked into the original trajectory. So this is how the neighborhood of a flow line looks like. A few times I mentioned that these flows are known to have a subtle relation to topology. So let me tell you a few examples of these relations. One of them is, let's say, Anosov himself. He showed in the early 60s that these flows don't have contractible periodic orbit. That's quite a fundamental fact. Thurston and Plante, I believe in 72, they showed that the fundamental group of the underlying manifold needs to have exponential growth in this case. If you don't know what exponential growth is, let me just say that that means that the fundamental group should be very, very large, which automatically would exclude the existence of these flows on like manifolds like S3 or like the torus and so on. So because their fundamental group is not large enough. And finally, Gis and with another proof, Barbo later on, they showed that, if you have a Seifert fibered manifold up to going to a finite cover, any Anosov flow would be equivalent to a geodesic flow example, which I discussed. Okay. So it turns out that the existence of an invariant volume form has some like deep consequences on the flow. So in order to see that, let's first start with the observation that both of the classical examples that I discussed, they have invariant volume forms by their natural construction. And the existence of this invariant volume form, even from like very classical dynamical system, would imply that these flows are transitive. When I say classical, I think that we can conclude that from the Poincare recurrence theorem. And when I say transitive, that means that there exists a dense orbit for this flow. Okay. So the existence of of invariant volume form would imply that these flows are transitive, and it's natural to ask, considering the two examples I gave you were volume preserving, it's natural to ask whether any Anosov flow is volume preserving, and the answer is that clearly not, because we can always perturb an Anosov flow. Okay, so how does that work? So just take one periodic orbit of one of the two flows, let's say in the previous example. So let's say this is the periodic orbit, and look at the Poincare linear map. So if you look at the Poincare linear map, let's say this is the tangent space here, and the Poincare linear map would have like two eigenvalues, one of them lambda s and the other one lambda u. Lambda u. Notice that the eigenvectors are again the unstable and stable directions, and just the volume preserving would imply that the determinant of this Poincare linear map, which is the multiplication of these two eigenvalues, should be equal to 1. So all you need to do to get an Anosov flow which is not volume preserving is just to simply perturb this like flow around this periodic orbit, so that this the multiplication of these two eigenvalues corresponding to unstable and stable direction is not equal to 1. So that flow definitely cannot be volume preserving. But that's not a great answer, because in some sense, this new flow that I got from this perturbation is in some sense equivalent to the original flow I started. What does that mean? That's because of this structural stability of these flows, which tell you not only the perturbed Anosov flow is Anosov, but it's also orbit equivalent to the original flow. So what does orbit equivalent mean? That means that there exists a homeomorphism sending orbits to orbits. So of course, you can't expect a diffeomorphism here because a diffeomorphism would also respect these eigenvalues. But as long as you care, as long as you care only about like the structure of these orbits, these two orbit structures are in some sense homeomorphic. So in some sense, I cheated and I didn't really give you a new flow when I was, saying that. So now I can turn the question, in order to find like non-volume preserving Anosov flows. Okay, so how can we find an Anosov flows which doesn't have the same topology of volume preserving one? In order to answer that, we can just go back to this statement that I said, the classical fact. It turns out that the inverse of this is also true. That's the theorem of Asaoka, which tells you that if you have a transitive Anosov flow, then it's orbit equivalent to some volume preserving Anosov flow. So we can kind of replace this condition with the condition of transitivity. So the question turns to, can we find non-transitive Anosov flows? It took more than 20 years to answer this question. Frank and Williams, they constructed the first examples of non-transitive Anosov flows. And Brunella in, I guess, 93, he basically showed how we can think of non-transitive Anosov flows in terms of the transitive ones. And that's basically because of this picture. If you have a non-transitive Anosov flow, you have a finite number of basic sets, which means that they're compact subsets of the manifold, where in that compact subset, you have a dense orbit. So in that compact subset is in some sense transitive, and you have incompressible, transverse incompressible tori separating these kind of parts. So basically that tells you that you can break any non-transitive Anosov flows into a bunch of transitive pieces, and that's how you can think of Anosov flows, general Anosov flows. Okay. Okay, great. So I think that's probably the longest I can go without mentioning contact and symplectic geometry in this talk. So let's see how we can bring contact and symplectic geometry into the picture. I'm going to just mention a few facts about contact geometry. I know that there are lots of experts in the audience, so I apologize for that. But just to make sure that we're on the same page and with the same terminology, I'm going to call a one form alpha a positive contact form on M if alpha wedge d alpha, which is is a three form, is positive on M compared to the orientation that M has. If it gives you a negative volume form on M, then we would call that a negative contact structure. And we call the kernel of this one form co-orientable positive or negative contact structure. I'm going to drop the co-orientability of this contact structure. I will make a comment on that later on. And this pair M and this equipped with this plane field is called a contact manifold. So notice that by Frobenius theorem, that means that C is simply a maximally non-integrable plane field. So in some sense, you can think of contact structures as the polar opposite of foliations, whether this non-integrability is positive or negative. And to give you a basic example, you can always think of what we call the standard contact form on R3. If you look at this one form, it's easy to check that alpha wedge d alpha is just the standard volume form on R3. And so that's a positive contact structure, and you can simply just sketch the kernel of this contact structure. Here you see the plane field restricted to XY plane, and notice that the plane field is invariant in the Z direction. Okay, similarly, you can give a standard model for negative contact structures, and you have this celebrated Darboux theorem, which tells you that this is all contact structures look like this locally. So that also means that their subtlety is should be more of a topological nature. Okay. But since we're talking about dynamics, well, that would be great if we can approach these geometric structures from a dynamical viewpoint. And that's exactly what Reeb vector field would do for us. So given a contact from alpha, there exists a unique vector field R alpha satisfying these two conditions. First of all, if you just plug R alpha into D alpha, you get 0. And also alpha of of this vector field is also equal to 1. So notice that from these two properties, that means that first this Reeb vector field should be transversed to the contact structure or the kernel of alpha because of the second property. And it's also very easy to see that this Reeb vector field, sorry, this is R, would also preserve the contact structure. Well, let's say it even preserves the contact form, so definitely it preserves the kernel of alpha. Okay, and it turns out that for any flow with these properties being transferred to the contact structure and preserving the contact structure, you can show that that's a Reeb vector field for an appropriate choice of contact form. In the previous example, in R3, you can easily see that this Z direction is a direction which is transverse to the flow, and it also keeps the flow, it's transverse to the contact structure, and also it keeps it invariant. So easy to compute that the Reeb vector field in the previous example is just a Z direction. So this is called Reeb vector field for C. And it gives us a kind of dynamical viewpoint to study contact structures. Let me just point out that, at least starting from like early 90s, from the work of people like Hofer, Wysocki, Zender, and so on, and later on in the introduction of contact homology, these flows are known to give you information of the topological aspects of contact structures as well. Okay. And okay, so how can I connect this to the discussion about like Anosov flows? Well, there's a very immediate connection to Anosov dynamics, and that is to study when Reeb vector field is Anosov. And these flows are called contact Anosov flows. And in this case, this this ESS and EUU directions, if you add them up, you will get a contact structure. And of course, these flows would be volume preserving Anosov flows, because if they preserve alpha, they would also preserve alpha with D alpha, which is a volume form. So that's a special case of volume preserving Anosov flows. And just to give you examples, the example on the unit tangent space of hyperbolic surfaces, the geodesic flows, that you can easily see that would give you contact Anosov flows. And by now we know that we have many more examples, including on hyperbolic manifolds of like these contact Anosov flows. But that's the most kind of immediate and straightforward way to connect contact geometry and Anosov dynamics. But actually, that's not really the direction I'm going today. This is a very subtle and deep, subfield in Anosov dynamics. There are lots of literature on contact Anosov flows. But today, I'm actually interested in a more general relation between contact geometry and Anosov dynamics. And that is mostly thanks to an observation that Mitsumatsu and independently Eliashberg-Thurston made in mid-90s. They showed that if you have, it's very actually easy to observe that it's not really a theorem, let's call it just a proposition. They show that if you have an Anosov 3 flow, then that the vector field generating that flow would lie in the intersection of a transverse positive and negative contact structures. So how can we see that? So if I claim that's just a proposition, I should have an easy way to show you that. So let's take a look at the picture we had for Anosov flows. So if you take let's say the bisector of, let's say, ESS direction and EUU direction, let me call that L plus. And you take a look at the action of the flow on this bisector. The action of the flow would just push this bisector towards the EUU direction, right? That's what you see in the picture. And similarly, if you take the other, bisector L minus, let me call that L minus, and look at the action of the flow, you can easily see again that the flow is kind of pushing this L minus again towards EUU direction. And the rotation that you see, so is basically the same rotation that you see in the Frobenius, in the definition of contact structures, via Frobenius theorem, which means basically that L plus, if you add it to the direction of the flow, that would be a positive contact structure. And if you look at L minus and add the direction of the flow, that would give you a negative contact structure. And obviously by construction, these two contact structures are also transverse. Their intersection is in fact the direction of the flow. Okay. And again, notice that I'm using the nice fact that these plane fields, the stable and unstable plane fields are C1. Otherwise, these bisectors would be C0 only. Then you would need to approximate, which is not hard for this proposition, but can be challenging in the later on. Okay. Just notice that the only remark I should make here is that, of course, if ESS is not orientable, then these like bisectors would not be orientable neither. So in order to, if I want to stick to the definition of contact structures as co-orientable plane fields, then I should also assume that these two directions are also orientable. If one of them is, the other one is also orientable, which is always the case, assuming that the manifold is orientable, is always the case, possibly after going to a double cover. Okay, so I'm gonna stick to this assumption, although more or less everything I say can be reformulated, kind of a little bit uglier in the case where these are not orientable, but let's stick to that. And also I call this pair of positive and negative contact structures, I call that a bicontact structure supporting my flow. Okay. So that raises an obvious question that, okay, if all Anosov flows are in the intersection of a pair of these two contact structures, is the other way correct or not? If you have a flow whose generating vector field lives in the intersection of two contact structures like this, can we conclude that that's an Anosov flow? And the answer is no. But before getting there, it turns out that this condition has some dynamical interpretation. So if you look at this theorem or proposition at the very end, I'm stating that this vector field lying in the intersection is if and only if it satisfies this definition, which is a more or less dynamical definition, more or less in the same with the same taste of the definition of Anosov flows. So let's take a look at this. So we call a flow phi generated by this vector field X a projectively Anosov if it's induced flow on this normal bundle. So the flow would induce some sort of action on the normal bundle of the direction of the flow. And then for this action, we need to have a splitting again into two line bundles. So notice that this normal bundle is two-dimensional now. So I can split it into two line bundles where again the splitting is continuous and invariant under this action. And if you take a vector in the ES direction and another vector in the EU direction and look at the action of the flow on these two vectors, then the length of the ratio of the length of these two vectors would increase exponentially. Okay, so this is quite weaker than maybe if you don't have intuition, we don't know how much weaker than Anosov flows is, but from the definition, it's clearly weaker because you're only controlling the ratio of the length of these two vectors. And so that means that, for instance, you can have a vector in the ES direction. The length of that vector might be increasing, but even if the length of that vector in the stable direction is increasing, the other vector in the EU direction would increase even faster at that time. So that the ratio of their lengths is increasing exponentially. And just to kind of have an intuition of why this is equivalent to this like picture of having a bicontact structure, you should just notice that this, the ratio of like this expansion, if you expand here more in the EU direction than ES direction, that's exactly what makes this kind of bisector tilt towards the EU direction, the ratio between these two expansions. Okay, and it turns out that, as I said, this dynamical definition is equivalent to this property, which is a purely contact geometric property. So the next question would be natural. Before getting to the next questions, as I said, you might say that, okay, maybe, like these two, although like the definitions are different, maybe, all projectively Anosov flows are Anosov. So I should give you an, non-Anosov examples, and it's very easy to build that on just torus. And we know that there are no Anosov flows on torus, so the vector field that we get, the projectively Anosov flow that we get here would definitely be an example where you don't have Anosovity. So if you look at these two contact structures, C plus and C minus, so probably you've seen these contact structures before. These are like the tight contact structures on the torus, and thinking of them as, just a perturbation of this horizontal foliation defined by dz. So we're just perturbing this foliation into a positive and negative contact structure, and this epsilon here would tell you basically the angle between this plane field and the horizontal foliation. And as long as this epsilon and the other epsilon prime for C minus, they're not equal, which means that these two plane fields would have different angles with the foliation, which in particular would mean that these two plane fields are in fact transverse. The previous proposition would tell you that any vector field, any non-vanishing vector field in the intersection would be a projectively Anosov flow. And as I said, we can be sure that this is not actually Anosov. So this is an explicit example, but let me just mention, without going that deep into it, that we have many over-twisted examples as well, even on S3. And so in some sense, the reason that projectively Anosov flows, unlike Anosov flows, are abundant and kind of flexible and so on, is more or less the same reason that over-twisted contact structures are abundant and so on. So, but the natural question we can ask here is that, okay, so now we have some sort of characterization of Anosov, projectively Anosov flows purely in terms of contact and symplectic geometry. Can we characterize Anosov flows in terms of contact and symplectic geometry? In order to see how that works, I'm going to give you a very kind of natural definition. Using the above definition, we can basically measure, like in terms of calculus, measure the expansion rate in the direction of stable and unstable, directions. So we just define our S as just the derivative of, the length of this like ES kind of growing as you under the flow. So we're just differentiating how fast like that vector is growing. And similarly, we can just do that with a vector in the EU direction, in the unstable direction. So if you remember what projectively Anosov flows are, the definition was that we have some sort of, the ratio of the length would be growing. If you translate it into this notion, that would mean that the RU is always bigger than RS, right? And you can also kind of guess what Anosov flows would mean in this context. That would mean that having a positive RU, which gives you absolute expansion in the EU direction, and negative RS, which tells you that you have absolute contraction in the stable direction. So that's quite natural, and from there we can just give you a characterization of Anosov flows in terms of Liouville geometry in order to see that. So we can, this is how basically we translate the metric information into like kind of in the language of like differential geometry and contact geometry. So we have this metric, we just define alpha S by this property that alpha S of ES, which is just the unit vector in the stable direction, is equal to 1, and alpha S would vanish on the, the other foliation. And similarly, we can define alpha U, and then define alpha plus as alpha U minus alpha, alpha S, and I'll define alpha minus as alpha U plus alpha S. This is, again, if you think of it, this means that the kernel of these, the kernel, are exactly these two contact structures here. And now consider this one form, which is linear interpolation of alpha minus and alpha plus on the manifold times interval. So look at, I parameterize this interval with T, and I interpolate between alpha plus and alpha minus using this extra parameter. And I can see very basic computation that the alpha, which now lives on, let me call this W, which is a 2 form on W, is just RU times some appropriate volume form, which we don't care about. Okay. So in particular, that means that the alpha is symplectic on W if RU is positive, which means that having absolute, expansion, or in other words, alpha is just a Liouville form. Okay. So just to give you a picture, maybe a better picture is to have this in mind. So consider this as M, interval across M. Look at one side of, one boundary component as M adapted with C plus, and the other boundary component as minus M adapted with, equipped with C minus. And now I'm just doing some sort of here, some sort of linear interpolation between these two. And I want this linear interpolation to be a Liouville. And if you want to see in this other picture, that would mean, if you want to see what happens in M, if you think of the kernel of alpha, that's just equivalent to linearly interpolating between these two plane fields as you move from one boundary component to the other boundary component, and you can do it in a symplectic way if this RU is positive. Okay. And similarly, just interpolate alpha plus and let's say minus alpha minus, and that would be again symplectic if RS is negative. So the other interpolation would be through the other plane field, and as you pass through that other plane field, the symplectic condition would be translated to having RS negative. Again, if you remember the previous slide, having these two conditions is equivalent to having an Anosov flow. Okay. So if I want to summarize that, I can say that this X is Anosov if you have two Liouville pairs, one of them alpha minus and alpha plus, the other one is minus alpha minus and alpha plus. And the kernel of these two contact forms is a supporting bicontact structure for my flow. So Liouville pairs, I'm defining such pairs as Liouville pairs. Pairs whose like linear interpolation would give you a Liouville form. And so notice that the second part is equivalent to being projectively Anosov, and this extra condition from Liouville geometry would guarantee Anosovity. And notice that also means that all the questions in Anosov dynamics, at least in principle, we can translate them into questions in contact and symplectic geometry. That's what this characterization is telling us. For instance, there are many different line directions we can go from here. For instance, the periodic orbits, if you of like these flows, would correspond to Legendrians for both C plus and C minus on the manifold, because the flow lines were tangent to both of these contact structures. And if you look at the interval times that periodic orbit, that would also give you some exact Lagrangian in the constructed Liouville manifold that I gave you. So what can we, how can we use like all the machinery that we have for Legendrian knot theory, Lagrangians, and so on? Now we can employ all of that, at least in principle, into the study of questions about periodic orbits of these flows. For instance, a question I'm interested in is to study the knot theory of these periodic orbits. That's something that there's not much known about. And another question, which is related to what I previously talked, is that we can now we showed that invariant volume forms have implications for the flow. So now, what does it mean, the existence of an invariant volume form in this context? Before answering that, let me mention that this also gives you all the nice properties for these contact structures like tightness, symplectic fillability, and so on. Okay, just as a side note, that's nice, but I'm not really going to use that today. Okay, so what does the existence of an invariant volume form mean in this context? In order to discuss that, I should tell you a little bit about the interaction with Reeb, the underlying Reeb flows. It's a very easy computation to see. We can basically compute where the Reeb flows are approximately in some sense. So here, if it's ESS and EUU, let's say, let's say, again, I look at this bisector here. And we can easily, but this is just, we can easily compute this, see that this vector field lies on this plane field. It's a very easy observation just from the fact that, just enforcing this condition would give you like this. But this very easy observation would even give you a kind of nice and useful characterization, again, of Anosov flows in terms of these underlying Reeb flows, because notice that the sign of this RS and RU would basically determine which quadrant this Reeb vector field is living on. So you can again see this is Anosov flow if and only if R plus is in the quadrant 2 or 4, if this is 1, 2, 3, 4, and similarly we can express that in terms of R minus. But this very simple observation would tell us that these two contact structures are also hypertight, because for taut foliations we don't have any contractible transverse line curve. And here these Reeb vector fields are, if it's Anosov, they're transverse to both of the foliations, and so they can't have a contractible periodic orbit. And just from the work of Hofer, Wysocki, Sender, we can get some like free corollaries from here. For instance, we can show that M is irreducible. These two contact structures are tight. M being irreducible and that's a very, very classical fact in Anosov dynamics, and these two contact structures being tight also gave that from the previous theorem. Also, it's nice to have a Reeb dynamical proof as well. And also it shows that you don't have any exact symplectic cobordism to the standard sphere, which I think is interesting because this is just a symplectic generalization of the non-existence of Anosov flows on S3. So we get some sort of symplectic generalization of not having Anosov flows on S3. Okay. Okay, so now let's go back to the to volume preserving Anosov flows. In this picture, the existence of a volume form would mean that the divergence is 0, which you can easily see that means that Rs plus Ru which is just a divergence. If you just add the expansion in the Ru direction, in the EU direction, with the expansion in the ES direction, naturally you get the divergence, and this divergence is 0 in this case. And again, if I draw that picture, that would mean that this Reeb vector field of C plus would lie exactly on this C minus if I take these two contact structures as kind of symmetric and so on. And similarly, I can show that in this case, the Reeb vector field for C minus, I can set things up in a way that also lives in C plus. Okay. And it turns out that that's quite easy observation. It turns out that we can actually prove the inverse as well. So if we summarize that, X is a volume preserving Anosov flow. If there exists a supporting bicontact structure, which is equivalent to projective anosovity, with this extra condition that these Reeb vector fields are included in one another. The inverse direction is a bit harder. We use some facts from dynamical systems, but essentially, again, we can get some sort of characterization. Just let me make another remark, which I forgot, was that in this picture also, when I'm going from anosovity to contact structures, I can set everything in a nice and symmetric way. But the inverse direction, again, here is a little bit harder because, the contact structures we start with, they might not have this nice, kind of symmetry. So for most of these things, the inverse direction is kind of harder, but the forward direction is easy to observe. Okay. So we get supporting, so we get also a characterization of the existence of invariant volume form in this case, in terms of this Reeb vector field. Okay. Well, how can we see that now? The point is that like having this invariant volume form, this is kind of forcing some sort of symmetry in this picture, which you can see in this picture, and also with this property, right? And well, it would be nice to see this symmetry in the previous picture that I discussed, in the picture of like this Liouville geometric picture as well. How does this symmetry kind of manifest itself in the picture of like this Liouville pairs? In order to see that this symmetry, we're going to see that the symmetry informed by this invariant volume form. We want to see it in the Liouville geometric picture. So again, recall that a Liouville structure on a 4 manifold is, as I said, that's when you have alpha such that the alpha is a symplectic on W, and then you have a unique vector field Y which satisfies this condition, and we call that a Liouville vector field. Okay. So naturally, I would like to see how does how can we compute this Liouville vector fields for this in this kind of Liouville pieces. If you have this invariant volume form, the computation would be very easy and also very symmetrical. You can see that this Liouville vector field would be just some reparameterization of the vector field, the generating vector field, plus some T component. or 2t delta t, around t, sorry. And if you want to see that, that means, what does that mean? Again, take a look at this Liouville picture. So if you look at the middle kind of fiber, which is kind of 0 times m, the Liouville vector, that is when t is equal to 0, the Liouville vector field is just some basically reparameterization of this flow. And as you move away from this 0 fiber, you will have like this t direction added. So the flow would be kind of unwrapped. Let me use another color. The flow would be unwrapped as you move away from the 0 section. And it, of course, you expect the Liouville vector field to flow out of the boundary component, and that's exactly what's happening in this picture. So that would give you some sort of symmetry in this picture, which I think is can be quite interesting. That would also justify, this definition, the next definition. So we saw that this reparameterization has some nice relation to Liouville geometry. So we just call that Liouville reparameterization of the flow, or also they also call that synchronization of the flow. And that is when you just reparameterize things in a way that this Ru and Rs, they're both constant, or let's say just one. Okay, that helps you actually compute things, and that gives you some like new questions that I think they're interesting. But in order to encapsulate what I just discussed, we showed that volume preserving Anosov flows, then there exists a reparameterization such that, first of all, this XL can be extended to a Liouville vector field on this interval times. And also with some more work, you can show that this transverse plane field is nothing but the plane field that you get from this Reeb vector field. So that means that this plane field that you get from these two Reeb vector fields in this case is nothing but just the ES S plus EUU. Okay. Let me also mention that we can have a function worth of pairs of Liouville vector field with this property that one is included in the other one. But if we want all the symmetry, we can just set things up like this, although the price we pay is that we don't have a great regularity, because these, these foliations were just C1. So the contact structures that we can build in a very symmetric way, they're just going to be C1. So even this Liouville form is C1, which is not great, but that's the price that we pay for this symmetry. But we can also break the symmetry and get some regularity if that's what we want. There are many, I think, interesting directions that we can go from here. So notice that this first thing, the first proposition, we can think of it as saying that this volume preserving Anosov flow can be thickened to a Liouville vector field. Of course, that thickening can be, you can thicken it to Liouville vector field in any dimension if you just add, just D2 and, direct sum just D2 and its standard Liouville form on it as well. So you can thicken this volume preserving Anosov flow to any Liouville vector field in any dimension. And in particular, it's interesting to try to understand this kind of the relation of this picture to Weinstein geometry, and that is because of the fact that notice that the skeleton in this picture, the skeleton is just the free manifold M, right? So obviously that means that this cannot be a Weinstein structure, because the dimension of the skeleton in that case should be at most half of the dimension. But that also means that if you add this summand, then maybe let me write it as D3 times M, and the vector field you get here might be you might be homotopic to a Weinstein structure. So adding this summand is called, kind of stabilization. So what I'm asking is whether we can understand the possibly Weinstein homotopy of these kind of stabilizations. So in particular, Christian and Breen, I guess last year, they showed that for suspension Anosov flows, after adding one of these summands, D2 summands, you can perturb things, you can deform things to become Weinstein. And now can we do that for all the volume preserving Anosov flows? So that's something I think interesting to discuss, trying to understand this Weinstein structure and understanding its skeleton, possibly its arboreal stratification, and possibly we can do that using, this two various tools that we have in Anosov dynamics. For instance, we have like things similar to open book decomposition. We have surfaces of section, so we have a good understanding of topology of volume preserving Anosov flows, and can we kind of relate that to the structure of the skeleton of this Weinstein structure. And another, for instance, very general direction to go is to understand the relation between these two contact structures and, and the flow itself. For instance, can we understand the Reeb dynamics, the relation between this Reeb dynamics, the underlying Reeb dynamics, and the flow itself? I showed that these Reeb flows, they don't have contractible periodic orbits, which is a similar property to Anosov flows. So that means that in a very weak sense, to some degree at least, they're mimicking the hyperbolic behavior of these Anosov flows. Naturally, we can ask whether this similarity can be furthered. And let me also say that, for instance, we can also discuss relating these two contact structures directly to themselves. Can they have, different contact homologies, for instance? Well, that is, these are all more or less kind of wide open. Well, they're not necessarily super hard. They're just, they haven't been discussed. Again, just to put some question here, just trying to understand this Liouville piece, the holomorphic curves inside this Liouville piece, and how we can use these holomorphic curves here to kind of relate the kind of contact homology on these two boundary components. Well, again, that's quite, we can make many questions about that. I think I'm basically out of time. I didn't have time to discuss the relation to surgery theory, but we can also kind of develop some sort of surgery theory for this setting, which is mostly being done by Federico Salmeraghi. But I'm out of time, so I'm going to stop here. Thank you so much.
Great, thanks so much for the talk. Let's give Surena a round of applause.
Thank you.
Are there any questions for the speaker?
Yeah, I had a question. You mentioned at some point in the talk these questions about like nodding phenomena. Like I was wondering, does the anosovity play? How does it play with sort of asking questions like nodding or linking of orbits?
Yeah, absolutely. So as far as I know, we know quite little. I think I'm going to put down the probably most famous theorem here, and they show that this is a theorem to Fenley and Barthelmy. They show that if the flow is R covered, which I'm going to explain in a second, then if you have two periodic orbits which are homotopic, then they show that they're isotopic as knots. And here, what is this extra condition R covered? R covered means that we had these two foliations. R covered means that the lift of these two foliations to the universal cover is just trivial foliation of the of R3 on R3. So with this extra condition, they show that you have like this kind of like isotopy between two homotopic periodic orbits. But I think there are like good reasons to believe that should be true in general, because the way that they use this R coveredness is basically some simplifying condition on these foliations in the fundamental, in the universal cover, right? But if you look at this in terms of contact geometry, the universal cover, the contact structures are both the standard contact structures on R3. So from the viewpoint of contact geometry, you have like the negative contact structure on the, on the universal cover, and positive contact structure, standard contact structure on the universal cover. So can we, for instance, use this fact to generalize their theorem for a general Anosov flow? Or in a more general sense, what can we say about the knot theory of these flows? Maybe we can get some, I don't know, obstructions on what knot classes can be represented by periodic orbits and so on. As far as I know, we don't know much about these types of questions.
I see, that's very interesting. I was also just curious, like, how many sort of examples are there of these Anosov flows where the two, so related to this question of like whether the two contact structures could have, like, for example, different contact homology, like, are there many examples where like the two contact structures are something that are really understood well? Like, are there a lot of examples where they are the same, or?
I believe the only examples which are kind of done explicitly and thoroughly are like the classical examples, the suspension flow and the geodesic flows. These two examples, I think they're pretty known and like written down in explicitly, but we don't really know anything more than that explicitly. We have many examples of contact Anosov flows, but the Anosov flow itself is, a Reeb vector field. But I haven't seen many discussion on how, like, these two other contact structures are, kind of playing along. Yeah. But I think the general kind of line of question is that, we have a very explicit model in this case. We have, especially in the volume preserving case, we have a very, very special, very explicit model. And well, I didn't tell you, but even on the manifold itself, when the flow is volume preserving, okay, so you have like this structure, but even on the manifold itself, you have something like an open book decomposition. You have a surface of section for the Anosov flow, which is again surface of section, of course, means it's tangent along the boundary, and some transfers on the surface. But notice that if the surface of section is tangent to the flow, that means that it's also tangent to the contact structure. So that's kind of like the difference between, it's a little bit different from the use of open book decomposition in contact geometry, where the boundary components are transfers to the contact structure. In this case, they're tangent to the contact structures, which also suggests that maybe we can use some basic convex surface theory and characteristic foliation type of thing on this surface of section. Again, that's something that, as far as I know, no one has really approached, and these are some of these questions might be easy to answer, some of them harder, but we just don't know much.
Other questions for the speaker?
On the relation to contact, oh, sorry. I mean, let me finish something related to the previous question. On the relation to contact homology, let me also just mention that if X is contact Anosov flow, then we know that the cylindrical contact homology, has like exponential growth. And the reason is that basically it's fairly straightforward using like Conley-Zender indices and so on. It's very straightforward to show that the differential is just trivial in this for the cylindrical contact homology in this case. And so since like the periodic orbits themselves are growing exponentially, that would also mean that the contact homology, the cylindrical contact homology would grow exponentially, which is like this is like cylindrical contact homology way of exhibiting chaos in the Anosov for an Anosov flow. But again, we don't know anything, as far as I know, we don't know anything about the contact homology of these two other contact structures and what kind of information they tell us about the underlying flow. Sorry, I just want to complete that. Yeah.
That's really interesting. Can you say more about this last slide about connections to surgery that you wanted to say a bit more on?
Yes. So surgery theory has also played a very significant role in Anosov dynamics. Many historically important questions were answered by introducing new surgery methods, where all of the surgery methods are in many ways they're the same in essence. That you usually cut along some annulus and then try to glue back with some dent twist. But because all of them are developed with different motivations, they're kind of not exactly the same. So it's natural to try to, now that we're developing some sort of contact geometry theory of these flows, it's natural to try to understand some surgery theory in this context and hopefully unify all the previous surgery operations. This is something that is being done mostly by Federico Salmoiraghi. And here, for instance, just the picture I gave you, we can see more or less how we can kind of use this. We saw that for this volume preserving Anosov flows, we have these Reeb vector fields included in the other contact structure. So just take some periodic orbit gamma and just, for now assume that the Anosov flow is volume preserving, which is not really necessary. So if you just push this periodic orbit along one of these Reeb vector fields, we get a family of knots which are Legendrian transverse in the sense that, okay, the Reeb R plus is Reeb vector field for C plus. So the knot is going to stay Legendrian for C plus, right? So it's going to be Legendrian for C plus, but R plus is a Legendrian vector field for C minus. So if you just push in that direction, the knot will become transverse to C minus. And you get basically an annulus, and this annulus, Federico shows that on this annulus, we can get very nice coordinates, which helps us apply the contact geometric surgery theory in this context. So we do a Legendrian surgery for one of the contact structures and transverse one for the other one. Federico shows that the resulting flow is Anosov, and he uses the fact that this characterization in terms of Reeb flows, because he uses the fact that we can, even after the surgery, we can guarantee that this Reeb vector field is going to stay in the other contact structure. So he controls that, and it turns out that all I used was just having just one of the Reeb vector fields included into the other contact structure along the periodic orbit. So if we just show that for a general Anosov flow, which is, if you care about there are some regularity issues, but if you resolve that, that's not very surprising. You can apply this surgery theory of this contact geometric surgery theory on any Anosov flow. And this is exactly a what is called a Goodman surgery in the classical, Anosov dynamics. One of the things that maybe a caveat, which is probably worth noting, is that there is some sort of there's some nice thing about this criteria in terms of Anosov flow, because almost always Anosovity, to show that the resulting flow is Anosov, almost always you kind of cut through some transverse annulus, and you do some sort of, after caring about some things, you do some sort of kind of interpolate the metric in a way that it stays Anosov, shows that the vector field is stays Anosov. But the nice thing here is that, if you just show that R plus is included in C minus, that's enough to show that the flow is Anosov, because I showed that if R plus is in like quadrant 2 or 4 of like the picture, this is the flow is Anosov, which is the case if you control this condition. This helps us to do surgeries on, let's say, analytes which are not transverse to the flow, and let's say they're tangent to the flow. And for that reason, I think this can also help us to apply surgeries, at least guarantee anosovity of the resulting flow in situations which we were not incapable of before.
Oh, well, thanks so much. Let's give Surena a hand for the great talk. Thanks very much.